In the last video, we talked about looking at integrals of the form sine to the m of x times cosine to the n of x dx. And we talked about the relationship between sine and cosine. Here we're going to talk about the relationship between the tangent of x and the secant of x. And they are similar to how the sine and the cosine are related through their derivatives. The tangent and the secant are related through their derivatives as well. So the derivative of the tangent of x is secant squared, and the derivative of the secant is secant of x times the tangent of x. These two trig functions are also related through identities. So the most fundamental of identities that connects them is 1 plus the tangent squared of x is equal to the secant squared of x. So how do we put those together and come up with an integration strategy for trig integrals that have tangents and secants in them? Well, let's pull up a strategy sheet. So this strategy sheet is going to rely on those connections with the derivatives that we just mentioned and that identity that we were talking about. And so if the power on the secant is even, so if the power on the secant is even, what we're going to do is we're going to pull off a secant squared and we're going to save it for later because we're going to do a u sub and we're going to end up using that as part of our u sub in order to do our u sub. So if we have an even power on secant, we're going to pull that off. We're going to save it like a little treat for later. Similar strategy to when we were working with sines and cosines. We pull that secant squared off. We convert whatever is left over into tangent using the identity, the relationship between secant squared and tangent squared through the identity. And then we make a u sub where u is the tangent and our du is that secant squared that we saved for later. So here, this one is kind of a specific criteria, but if m is odd, so if the power on the tangent is odd, and n is greater than or equal to 1. So basically, if we have at least one secant and the power on the tangent is odd, what we're going to do is we're going to pull off a secant and a tangent. So we're going to pull a secant tangent off. We're going to save it for later. That's going to be for our u sub that comes later. We're going to convert whatever's left over into secant using whatever's left over of the tangent into secant using the identity. So we take the identity tangent squared of x equals secant squared minus 1, and we make a little conversion from our tangents into all secants, and then we use a u sub where we let u be equal to that secant, and we've pulled that du off to the side, so we'll be able to make that substitution. Now, that, of course, is not going to cover all of the cases on the powers, right? Those are just two specific powers. If n is even, if m is odd, and we have at least one n, n is at least 1. The other cases are not quite as clear cut. And so, again, just sort of manipulation and playing around with the facts that connect secants and tangents is what we will do in those cases. I'm going to go ahead on this video and prove these three that use some creative, shall I say, techniques, some beyond the basics integration techniques, but nothing that we haven't seen before. So we will prove these three using some u substitution, some integration by parts. I'm going to prove these three integrals, but these three integrals do become useful integrals for us, and we're going to add them into the list of integrals that are helpful for us as we're doing our work with integration. All right, let's jump into some examples. All right, on this first example, the integral of the tangent to the fifth of x times the secant to the sixth of x dx, the power on the secant is even. So we see that that power is even. Power on the secant is even, which means I can pull off a secant squared. So that's what I'm going to do. I'm going to pull off a secant squared. Remember, we're just sort of saving it for later, like a little treat that we will need to use later. Okay, so I separate. What I have left behind now is secant to the fourth. So what I can do with what's left behind is, first of all, I can think of that as secant squared of x squared, since that was even, when I pulled secant squared off, I was still left with an even power there, which means I can convert it into the secant squared raised to some power. And I know, and I just rewrote the identity over here, but I do know this is just that fundamental identity. That fundamental identity right there says that secant squared is just 1 plus the tangent squared of x. So I can make that substitution there for secant squared. Everything else I'm going to leave alone. I'm converting what was left of my secants into tangents. And I have this secant squared of x that I've pulled off. and I'm just letting it sort of float out here, sort of sit out here for this very next step where I'm going to go ahead and say let u equal the tangent of x, because now that I've converted what was left behind, if I let u be my tangent, the derivative du is secant squared of x dx, but I have that secant squared sitting right out here. So I can make those substitutions. This becomes u to the fifth times 1 plus u squared squared, and the secant squared dx is my du. So doing those little steps, pulling that secant squared off, converting what was left into tangent, gives me the ability to do this right here where we made that u substitution. I now have an integral that I can integrate. I do have a little bit of algebra to do here, so I'm going to go ahead and expand that out. That's u to the fifth. This is 1 plus 2u squared plus u to the fourth du. Keep going with my algebra before I can integrate. U to the fifth plus 2u to the seventh plus u to the ninth du. And now that becomes u to the sixth over 6 plus 2u to the eighth over 8 plus u to the 10th over 10 plus my integration constant. And now I just put my u back in. So this becomes tangent to the 6th of x over 6 plus, that becomes a 1/4 when I reduce. So it's tangent to the 8th of x over 4 plus tangent to the 10th of x over 10 plus that integration constant, and doing that little manipulation by pulling that secant squared off, converting everything that was left into tangents, allowed me to make that u substitution and integrate. So that's if we've got an even power on the secant, that is our strategy. Okay, what do we do in this scenario? So notice here we have tangent to the fifth of x times secant to the third of x. So notice that we have an odd power on the tangent, and we have at least one secant. So in that scenario, what I do is I pull off one tangent and one secant. So what I have left behind here, I'm going to end up with a secant of x times the tangent of x dx. And again, I'm just sort of leaving that, right? I'm just pulling apart this integral a little bit. I'm leaving that so that I will have that for later when I make a u substitution. So I do that, and then I come and I look at what's left on the tangent. So what's left on the tangent, tangent to the fourth, is the tangent squared of x squared. And I know I've put the identity over here. Hopefully we have this identity memorized by now. But I have this identity over here, and I could solve for the tangent squared of x. I can convert a tangent squared into secants by using that identity. I'll just subtract 1. Tangent squared of x is equal to the secant squared of x minus 1. So I can make that substitution, secant squared of x minus 1 squared. We still have the secant squared of x and the secant of x tangent of x that we'll just carry down. But we're leaving that secant x tangent x over here because I'm going to need it for this very next step, because now that I've converted everything else into secants, I can go ahead and say let u equal the secant of x, and then my du is the secant of x tangent of x dx, and I can make those substitutions because I strategically pulled that secant x tangent x off in the beginning based on the powers. So now I've got u squared minus 1 squared times u squared, and there's my du. So my du is sitting there conveniently based on how I pulled that off. Now, once again, I'm now in a spot where I just have a polynomial in u. I need to expand it, and then I can integrate. So this becomes u to the fourth minus 2u squared plus 1 times u squared du. Keep expanding, so I get u to the sixth minus 2u to the fourth plus u squared du. And then integrate, I get u to the seventh over 7 minus 2u to the fifth over 5 plus u cubed over 3 plus my integration constant. Nothing reduces, but I'll put my secant back in. So that's secant to the 7th of x over 7 minus 2 secant to the 5th of x over 5 plus secant to the 3rd of x over 3 plus c, and I'm able to find my integral once again by relying on the relationships between secant and tangent, both in their derivatives and in their identity. Okay, but what if it's not one of those specific scenarios that we just talked about in those last two examples? What if it's something like just the tangent of x? Well, I actually think we might have done the tangent of x on a previous video, but let's go back to one strategy is just to convert back into sines and cosines and think about, well, what could I do if it was in terms of sine and cosine? And as soon as I write that, I notice that my denominator, if I let u equal the cosine of x, then my du is negative sine of x dx. So sine of x dx is equal to negative du. And I can make those substitutions, and this works into negative 1 over u du, making those substitutions, and that is integrable. I can integrate that. That's just minus the natural log of the absolute value of u plus c, which that's just the natural log of the absolute value of the cosine of x plus c, and we could leave it in that form. But again, remember we have all these relationships between tangent and secant, both through their derivatives and their identities, but their integrals also have relationships. So let's look at this. This is really like a -1. And so if I just use some algebra here and I bring that in as an exponent, this becomes the natural log of the absolute value of the cosine of x to the negative first power. And that is the secant of x, because that's 1 over the cosine. So it turns out that the integral of the tangent of x dx, remember that's 1 over the cosine of x, and so that becomes the natural log of the absolute value of the secant of x plus c. And that, let's go ahead and box it in and highlight it. That is the integral, just use that's the proof of the integral of the tangent of x. But that is one that is worth, let's give it some fireworks, because that is one that is worth memorizing so that you don't have to prove it every time you come across it. This is what I would say is a useful integral, meaning worth memorizing. Put it on a flashcard or something and take a look at that one. That one we should add into, just like we know the integral of the sine and the integral of the cosine, the integral of the tangent is the natural log of the absolute value of the secant. Okay, so that was just sort of, that's one strategy, right? When we come across a trig function other than sine or cosine, if we convert into sines and cosines, sometimes that gives us a clue. All right, let's take a look at this guy, this integral of the secant of x. Now this one, we're going to use the algebraic trick of multiplying by a fancy 1. And I am going to be specific here, secant plus the tangent of x over secant plus tangent. Now, why would I do that, right? This is, again, that multiply by 1. I'll make the 1 look kind of fancy. This is the strategy that we're working here. We're multiplying by a fancy 1. So why would I do that? Well, look at what happens when I do that. This becomes, on the top, this becomes the secant squared of x plus the secant of x times the tangent of x. Now I'm looking at that, and that is a derivative. Each of those terms is a derivative of a function. The derivative of the tangent is secant squared, and the derivative of the secant is secant times the tangent. Well, look at what the bottom is, secant of x plus the tangent of x. And that has been strategically set up now for a pretty sweet little u sub. U equals the secant of x plus the tangent of x, and du then would be secant of x, tangent of x, plus the derivative of the tangent is secant squared of x, and then move the differential dx. So look at that. That is exactly the numerator, and that is exactly the denominator. And we can make that substitution, and look at what happens. This just becomes the integral of 1 over u du. There's our du. It was just like cooked up just perfectly with that strategic choice for that fancy 1 that we multiplied by. So this then becomes the natural log of the absolute value of u plus c. This is the natural log of the absolute value of the secant of x plus the tangent of x plus c. And so the integral of the secant of x dx is actually equal to the natural log of the absolute value of the secant of x plus the tangent of x plus c. And that is, again, I'll go ahead and highlight it. That's just showing one integration strategy, that kind of strategic choice of a fancy 1 so that we can set ourselves up for a u sub. But again, I'm going to give this guy fireworks just like I did the last one, because in a similar way, knowing the integral for the tangent, knowing the integral for the secant can be useful in our work moving forward with integrals. So this is a useful integral. And again, I would suggest that we memorize. It'll save us time in having to prove this or look it up every time we need it. So the integral of the secant of x is the natural log of the secant of x plus the tangent of x. Okay, let's do one more. If I can find where I put it. All right, let's take a look at the secant cubed of x. So again, this does not fit in with our sets of rules. So what can we do here? Well, here what we can do is we can break this apart a little bit. I'm going to write this as the secant squared of x times the secant of x dx. And I'm going to think about that. I'm going to go ahead and I'm going to break that apart. I'm going to think of that. That's a product, right? So secant cubed is a product. I'm going to break it apart and I'm going to use integration by parts. And because I'm thinking about functions whose derivatives are easy to find and whose integrals I know, I'm going to work with, I know the integral of the secant squared of x. That's just going to be the tangent of x. And I know the derivative of the secant of x. So I'm going to go ahead and set up my integration by parts in that way. I'm going to break apart that product. I take that secant cubed. I'm going to break apart that secant cubed into a product, one of which I know the integral and one of which I know the derivative. And now I'm going to work with it. So now I'm going to say, well, then du is just secant of x times the tangent of x. And the integral of secant squared is just the tangent of x. We will have a dx in there too. I'm running out of space, but I'm going to squeeze it in there. And now I use my integration by parts. I'm going to multiply u times v and v times du. So I'm going to bring it all down here. So secant cubed of x dx is going to be equal to, remember my integration by parts tells me it's going to be u times v minus the integral of v du. So using an integration strategy we just learned, this is going to be secant of x tangent of x minus the integral of, now when I multiply those two together, I end up with the secant of x times the tangent squared of x dx. Now, this is again still a product, so I have to pause for a second and think about what can I do there with that product. But that's where I'm going to use an identity, because I see that tangent squared and I know the identity 1 plus the tangent squared equals the secant squared, so I could solve for tangent squared, and that's secant squared minus 1. And I'm going to make that substitution. So down here I'm going to make this the secant of x times the secant squared of x minus 1 dx. And I'm going to keep going. I'm going to distribute that. That becomes secant cubed of x minus the secant of x dx. And I'm going to carry down the rest of it. Secant tangent of x. I'm going to zoom in a little. I'm getting really small. And I'm going to go ahead and I'm going to expand that into two integrals. So the secant, still got just carrying my secant x tangent x term down. This becomes minus the integral of the secant cubed of x dx plus the integral of the secant of x dx. And now look at what has happened. This is something that happens periodically when we're working integration by parts. Look at what has happened here. We have cycled back to the original integral. So notice that this term is the same as what we started with. We cycled back to our original integral. Now when that happens, what I can do is I can actually add that integral to this integral, leaving me with two of those secant integrals of secant cubed of x dx. So that takes care of that term. We still have the secant of x tangent of x plus, well, wait just a second, we just found this integral. We know what the integral of the secant of x is. Let me scooch over here. The integral of the secant of x, we just on our last example proved that that was the natural log of the absolute value of the secant of x plus the tangent of x. So I can just use what I just rather than reproving that, right? That's why I said that's a useful integral. I can use what I just proved. That's the natural log of the absolute value of the secant of x plus the tangent of x. Now, of course, there's a plus c floating around through each of these integrations. I'm going to wait until the very end because right now we're going to divide by 2, so we'd be taking a constant and dividing by 2, which is going to be still just a constant. So we'll add in that constant at the very end. I'm going to multiply by 2 because remember we moved that secant cubed over, so our integral became 2 times the integral of secant cubed. And now we have proven that the integral of the secant cubed of x dx is equal to 1/2 times the secant of x tangent of x plus the natural log of the absolute value of the secant of x plus the tangent of x plus an integration constant. And that is, again, a useful integral. That one's a little bit more to memorize, and maybe we won't see quite as much as the other two that we just talked about being useful integrals. But there is some nice patterns in there. Let me get it highlighted and fireworked up for us so we can think of it as a useful integral. It's one we definitely want to have on our list of integrals that we've now proven and we could use, but I'll add useful integral. It will crop up in our work as we're doing integration. But one of the nice things to notice here is that the integral of the secant cubed has some little patterns here. Notice that this is the derivative of the secant and this is the integral of the secant. We add the two together and take 1/2. So, right, if we can remember the derivative of the secant and the integral of the secant, then the integral of the secant cubed is the combination of those two things and then 1/2 of it. Just like a little way to remember it, I guess. But it is a useful integral. If you can memorize that one, that could save you some time, but definitely want to add it into our list of integrals that we've proven, so when we come across secant cubed, we'll be able to quickly integrate it. Okay. I wanted to end this video by just stating that we have looked at the relationship and the integrals that combine sine and cosine, and now we've looked at also because the tangent of x and the secant of x have combinations and relationships in their derivatives and their identities. We've looked at integrals with tangents and secants in them. We could, in a very similar way, extend the theory because the cotangent of x and the cosecant of x similarly have relationships in their derivatives and in their identities, as I have right here. So the integral of cotangent m to the x, cosecant n to the x dx, we have similar strategies that can be derived using their derivatives and their identity that connects them, their fundamental identity. So I'm not going to go into the details here on this video, but just remember that there is similar connections between those two functions that can be expanded upon when you're integrating as well.